Hello everyone, this is Hariharnath. Have you ever tried to measure current in nanoamps and your normal multimeter doesn't work? Today we'll build and demo a precision digital microcurrent meter that can measure currents as low as 2 nanoamps while still holding up to 300 milliamps. Let's start by simply asking, why do we need precision digital microcurrent meter and what is its purpose? When we develop ultra low power devices like medical wearables, smart meters, portable devices, etc., it is important for us to understand how much power it is consuming at various stages. A standard multimeter has less than or equal to 1 microamp resolution and high burden voltage that corrupts our results. Our microcurrent meter solves these problems. Before we begin, we'll have to gather all the necessary components that are required in this project. If you are wondering from where we get all the components at one place, then allow me to introduce to today's sponsor, that is Digikey. Digikey is an e-commerce distributor which is a global leader in cutting-edge commerce distribution of electronic components and automation products worldwide. They provide more than 16.5 million components from over 3,000 manufacturers with products in stock available for immediate shipment. Also, with their fast shipping and excellent customer support, you can always trust that your products will arrive on time and in top condition. So do remember to check out Digikey for your next project. This is the Digikey website and you can search by keyword or part number from here. So I'll open the BOM and try to find out the list of components. So here this is the BOM and by this link I can directly find or I can use the part number. So I'll try to show via part number. So this is the part, and same way we'll discuss some of the parts that we have used. The first one is STM32G071KB U6. So this is the microcontroller chosen for its robust ADC performance and peripheral flexibility. It is the brain of our meter, managing data acquisition, display control and power management. Next one is MAX 4239 AUT plus T. So this is the zero drift amplifier which is crucial for achieving high precision by continuously cancelling its internal offset. This is INA 333, so which is an instrumentation amplifier which helps convert the differential signal from our analog front end to be compatible with microcontroller ADC. So this is the LTC4054 which is a linear charger for our battery. All the components used in this project were purchased from Digikey and were shipped to India using their local logistic partner Enclosure. This way you know the grand total that you have to pay for your order, including shipping charges, GST and custom fees. You can just proceed with checkout and not worry about additional tax or custom clearance process, because all of this will be taken care by Enclosure and they'll ship it to your doorstep without need of any extra fee. This precision digital microcurrent meter ensures accurate measurement of very small currents as low as 2 nanoamps. It helps track power consumption in low power devices and systems. It is built around an STM32 microcontroller and features 128x64 OLED display for real-time readouts. The analog front end is designed to detect small current flows accurately, converting them into voltage levels that the microcontroller can process with high resolution. Whether you are measuring sleep current in a sensor node or characterizing a power efficient circuit, this device offers a clear and immediate view of power consumption trends. Now let's look into other features of microcurrent meter. This microcurrent meter has multiple measurement ranges such as nanoamps, microamps and milliamps. Nanoamp current range is up to 1000 nanoamps. Microamp current range is 1000 microamps. Milliamp current range is up to 300 milliamps. It uses Arduino based firmware for easy development, and this is battery powered with built-in charger. It also provides real-time display updates and has a soft power switch to turn on the meter. Now that we understood the features and importance of microcurrent meter, let's dive into the project. So this is the complete schematic where you can see the circuit diagram for precision digital microcurrent meter, and it is organized into different sections based on the functionality. So first we'll look into the power section. This block manages power and featuring USB Type-C input, and it has LTC4054 linear charger for lithium ion batteries and ADP44002 LDO for a stable 2.5 volt supply. It incorporates a soft latch power switch using MOSFETs controlled by STM32's PA4 pin for both powering on and off and button monitoring. Next is the heart of our circuit, which is STM32G071 KBU microcontroller. This MCU centrally controls data acquisition, display and power management. Specific analog GPIOs are configured to read current, virtual ground, optional precision reference and battery voltage respectively, while SWD and UART headers facilitate firmware development and debugging. Now let's talk about the analog front end of this project. Based on the microcurrent design, this section acts as a precision current to voltage converter, utilizing multi-range shunt resistors and an ultra-low offset auto zero op-amp, which is MAX 4239. The MAX 4239's auto zeroing eliminates DC offset and 1/f noise, ensuring accurate and stable amplification for extremely small currents. INA 333 instrumentation amplifier is added to manage the virtual ground outputs and provide differential to single-ended conversion compatible with STM32's ADC with gain set by precision resistors for consistent amplification. Now let's take a look at the PCB and 3D printed hardware enclosure. This is the microcurrent meter, and we have custom designed PCB measuring approximately 45 mm by 65 mm. The PCB supports both through-hole and surface mount components. We have a 3D printed enclosure that houses the PCB. With provisions for display mounting, switch access, the enclosure enhances portability and durability, giving the device a finished, user-friendly appearance suitable for benchtop or field use. Now let's look into the programming step. First, we need to open Arduino IDE. Because we are using STM32 core in Arduino IDE, we need to do certain configurations and also add a board separately. So I'll show you the steps here. So first step is to add a JSON in the additional board manager URLs. First, you need to copy this JSON and then go to Arduino IDE. You need to go to Files, Preferences, and here in the additional boards manager URLs, click on this and enter this JSON, which I have already entered. So click on OK and OK. So it will take some minutes to load them. Once that is done, you need to go to board manager. So this is the board manager and try to search for STM32. And here you need to use the first one, which is not having the version 1.0.0. So you need to check the version which is later one and take that and install. So I have already installed, that's why you can see like this. Once we have done this, we can review the code. So first we have used headers and some of the definitions. So this section will set up the project by including essential libraries for I2C communication and serial communication and OLED display. It also defines crucial components and variables used in this code. So next we have button interrupt service routine. This button ISR function is triggered by changes on the latch pin. It implements debouncing logic to prevent multiple triggers from a single press. So next is the setup function. This setup function runs once at the start. It configures latch pin as an input with pull-up resistor and attaches the button ISR to it to respond to the changes. It initializes serial communication for debugging output and sets the ADC resolution to 12 bits. Finally, it starts the OLED display by calling U8G2.begin. This loop function is the main execution block. Every 500 milliseconds, it performs a series of measurements. It calculates the VDDA and measures the battery voltage reference voltage and current sense amplifier voltage. It then processes these to derive the microcurrent, that is amp V and amp Vf, and the battery percentage. This section also handles OLED display updates and displays the calculated microcurrent value. Next, we'll look into some of the important measurement functions. So these are some of the functions where we are using for analog to digital conversion. The first one is measure VDDA, and this calculates the actual supply voltage VDDA for the ADC by taking multiple oversampled readings from an internal reference and using a known reference voltage. Next is the measure input voltage. This measures the voltage on specified pin by taking multiple oversampled ADC readings and converting them into millivolts using the calculated VDDA. Next function is oversampled ADC. It performs oversampling of readings and then averages them and finally scales the result to a 16-bit range. This section will calculate the battery level percentage. And next function is responsible for graphically representing the battery charge on OLED by giving a visual indication of the charge level. And then we need to upload this code by connecting our microcurrent meter and click on this button. Now that we have programmed the board, we have come to the most awaited segment of the video, that is demo of the microcurrent meter. To perform the demo, we'll first connect the microcurrent meter to a ESP32, which is in a deep sleep mode and measures its current. Later on, we'll connect microcurrent meter to various resistors to measure the current in milliamps, microamps and nanoamps and observe the current measurements on OLED display. Here we can see ESP32 is the device under test and it is in deep sleep mode. I have connected all the components as shown in the screen to measure its sleep current. Now we can see the multimeter is set in milliamps and microcurrent meter is also set in milliamps. We can now see the accurate readings of small currents which are in milliamps from both the meter. Next, we go with 10k ohm resistor as a load resistor and measure the current in microamp. So we will set the microcurrent meter to microamp and multimeter also in microamps. Here we can already see the accuracy of microcurrent meter and the multimeter is slightly showing a different measurement. Let's now use the 1 mega ohm resistor to measure the nanoamps readings. First, we'll configure and start the power profiler kit. We have also set our microcurrent meter to nanoamps and multimeter to microamps, as this is the least range we have in our multimeters. Now the measurement is started. You can see the power profiler measurements at the bottom right, which has the average current over a specified time window. We can see the accurate current measurements in our microcurrent meter compared to power profiler kit and multimeter. And that is the real differentiator of this microcurrent meter. These accurate results of small currents helps in analyzing the power consumption of any device under test. That's all for today's video. I'm Hariharnath. Thank you for watching and I'll see you in another interesting video.
Digikey.